Okay, in the previous lesson we looked at an object that was moving horizontally with some velocity v through the air, which gave it some resistive force, F sub r. And we said that F sub r was proportional to velocity, and that gave us an equation F sub r equals negative b times v, where the resistive force is opposite the direction of the velocity. That's where you get the negative sign. And b is a proportionality constant, which depends on things like the density of the air and the surface area of the object. So now we're going to use that same resistive force as proportional to velocity, but we're going to consider the object to be falling. So it's acted upon by a force of gravity that's equal to the weight, which is the mass times the acceleration due to gravity, g. And this resistive force, F sub r, is in the opposite direction. So these conditions right here, where F sub r is proportional to v and F sub r equals negative b times v, still hold the same. And that b, the units of b, it's not necessary right now to understand everything that goes into b, but the units of b are still going to be kilograms per second. We'll do a little dimensional analysis later to make sure we get our math right, and that's going to help us out. But let's start with Newton's second law and see if we can come up with a differential equation that will let us come up with an equation for the velocity as a function of time and then the position as a function of time. So we can say the net force, or the sum of the forces on the object, still equals ma, that's Newton's second law. And let's say that the positive direction is the direction that the object's moving. So it's falling, so that'll be in the direction of gravity. So mg is positive, and bv is negative. The resistive force is negative. And then we can do what we did before and say that acceleration is the derivative of velocity. So ma becomes m dv over dt, and that equals mg minus bv. And essentially, the physics portion is done there, and now we have a mathematical exercise. So let's see if we can go through the math here and come up with an equation v as a function of time equals some equation. Okay, before we do that, let's take a look real quick and look at one condition. What happens when the acceleration is zero? Now, we've all heard of terminal velocity, and that's when the object gets to a certain point and it stops accelerating, because at that point, the acceleration, the force due to gravity is equal to the force of the air resistance. So, when a equals zero, if a equals zero, if this right here equals zero, then we can move mg to the other side of the equation. And we find that velocity in that case, negative kind of goes away if you rearrange that. That case, our velocity, which becomes our terminal velocity, equals mg over b. We'll box that in because we'll use that later to make the math a little bit simpler to write out. So we can approach this problem right here, integrating this problem right here, the same way we did before. We're going to go through separation of variables. So I'm going to write this as m dv, and I'm going to get all the terms with v on one side of the equation. And I'm going to integrate that side, and all the terms with t on the other side of the equation. I'm going to integrate the left side from the initial velocity v sub 0 to some velocity at time t, we'll call it v, and the object's going to be at v sub 0 at time t equals 0, and we're going to integrate to time t. So those are our limits. Okay. So on the right, this is pretty easy. The integral of dt is just t, and if I take that from the limits of 0 to t, then it becomes t minus 0 equals t. So on the right, I've got t, no problem. On the left, let's remember that if I have the integral of du over u, where u is some function of some variable, I can solve that integral as the natural log of the absolute value of u plus c. Well, I don't quite have if mg minus bv is u, I don't quite have du at the top. Because in that case, du would equal negative b. Du equals negative b. So I need to adjust what I have for my integral up here until I have this. Well, what would be if mg minus bv is u? What would be the derivative? It would be negative b dv, actually. So if I put that negative b dv over mg minus bv, and remember that's multiplied by m, which I just left outside of the integral. Well, if I multiply by negative b here, I need to multiply by negative 1 over b on the outside. In that case, I'm multiplying by 1, and then I have my integral in the form of du over u. And then I can integrate. So I can say this equals negative m over b times the natural log of mg minus bv. And that goes from the limits of v sub 0 to v, and I can set that equal to t. And the first thing I can do is I can move this constant negative m over b to the right side, and I can say on the left side I have natural log mg minus bv minus natural log of mg minus b v sub o equals negative b over m times t. And I'm going to put a little note here that says let m over b equal tau. And remember, the units of tau are going to be kilograms over seconds, and that's going to be seconds. Now also remember, for our logarithms, log base b of a minus log base b of b equals log base b of a over b. So I can rewrite this as natural log of mg minus bv over mg minus b v sub o equals negative t over tau. If m over b is tau, then negative b over m is negative 1 over tau. Now remember how logarithms work. Log base b of y equals x means b to the x equals y. Well, our b in this case, since it's a natural log, is e. Our y is this expression in parentheses, mg minus bv over mg minus bv sub o, and our x over here is negative t over tau. So this lets me say that mg minus bv over mg minus bv sub o equals e to the negative t over tau. Now it's a matter of separating this out, solving for v, and not making a mistake in any of the algebra. So taking this step by step, mg minus bv equals mg e to the negative t over tau minus b v sub o times e to the negative t over tau Now I'm going to move that mg over. Negative bv equals mg e to the negative t over tau minus b v sub o e to the negative t over tau minus mg. Now I'm going to divide by negative b. v equals negative mg over b e to the negative t over tau plus b v sub 0, plus the b's cancel out, plus v sub 0 e to the negative t over tau plus mg over b. Now remember, mg over b is the terminal velocity. So I can write this again. V equals v sub t, that comes from here, minus v sub t e to the negative t over tau plus v sub o e to the negative t over tau. And I can factor out v sub t, the terminal velocity here, and I have an equation. Velocity as a function of time equals terminal velocity times 1 minus e to the negative t over tau plus v sub 0, the initial velocity, e to the negative t over tau. And that is an equation for the velocity as a function of time for an object falling with linear air resistance, where your resistive force of air resistance equals negative b times v. Okay, so that's the velocity function. Can we solve for a position function? Well, if we remember that velocity is the derivative of position, I can say dx over dt equals v sub t minus v sub t e to the negative t over tau plus v sub o e to the negative t over tau. And I can integrate this. I'm going to integrate from 0 to x, position x equals 0 to position x equals x, dx equals the integral from 0 to t of vt dt minus v sub t times the integral from 0 to t e to the negative t over tau dt plus v sub o times the integral from 0 to t e to the negative t over tau dt. And notice over here I wrote the v sub t constant on the inside of the integral, and over here I wrote it on the outside. Either way is correct, but if I'm integrating something here like e to the negative t over tau, it sometimes helps to keep it on the outside, so I know that I don't really have to keep track of this as I integrate. Over here on the left, if I integrate dx from x to 0, I get x minus 0. It's going to equal x. And over here, I'm going to get v sub t times t. And if I integrate that from the limits from t to 0, it just ends up being t, so we'll let that go for a second. And then minus, I'm going to put this in parentheses because I'm going to have to go to the limits here. Okay, so remember what happens when you integrate, or when you differentiate e to the f of x. It's f prime of x, e to the f of x. So what I have to do here is think about doing that backwards. So I would have, if I differentiated this, I would have negative 1 over tau. So what I have to have here to start with is negative v sub t tau. I have to multiply this by the negative tau so that I get this when I differentiate, times e to the negative t over tau. And that's going to be from the limits of 0 to t. And then I'm going to add negative v sub o tau e to the negative t over tau from the limits of 0 to t. So again, it's just trying to go through this and not mess up the algebra at this point. So x equals v sub t times t minus v sub t tau e to the negative t over tau I will go ahead and put this negative on the outside here and make that a plus because it's going to save me a little bit of trouble here, minus e to the 0 plus, again I have this negative here, so I'm going to put that on the outside, v sub o tau times e to the negative t over tau minus e to the 0, which is 1. X equals v sub t times time plus v sub t tau e to the negative t over tau minus 1 minus v sub o tau e to the negative t over tau minus 1, and I'm going to distribute that negative 1 over there and say x as a function of time equals v sub t times t plus v sub t tau e to the negative t over tau minus 1 plus v sub o tau 1 minus e to the negative t over tau. Okay, so let's do a little quick dimensional analysis here. Remember, we said the units of tau are seconds. So the units for v sub t, it's a terminal velocity, so that's meters per second times second, that's meters. The units for time are seconds, units for tau are seconds, so everything inside the parentheses is a unitless number. So here I have meters per second, there I have meters per second, and here I have meters per second. Oh, sorry, it's meters per second times second. Here I have meters per second times second. Here I have meters per second times seconds. So all of these come out to be meters. So I have an equation for the distance as a function of time, and the dimensions come out to be in units of meters or units of distance. So there I have my equations for velocity as a function of time and position as a function of time. And if I want to look at the graph, the velocity as a function of time is going to go up until it has an asymptote here that's going to be v sub t, and that v sub t again is going to be mg over b. And if I look at the distance as a function of time, It's going to start up here at some distance at time 0, and it's going to go through an exponential drop there. So that is your derivation for your velocity as a function of time and position as a function of time for linear air resistance, where your air resistance is proportional to the velocity. Okay, and we'll take a look at some problems with that in the next lesson, and then we'll take a look at quadratic air resistance.